Another pair of conjugate prior and likelihood is a Poisson Gamma pair. So when you have data that follows Poisson distribution, so you have a Poisson likelihood, then gamma prior happens to be the conjugate to it. And again, if you want to understand how to choose a prior for a given likelihood, you just have to write down the density function for the likelihood. So let's see, for the Poisson, you remember for a single sample, you have lambda raised to the power y, and then e to the power negative lambda divided by the y factorial. So now if you want to sum it up, or you have to actually take a product, I goes from 1 to n, so you're going to have yi here, yi here. So this is just a constant. The factorial, we're just going to ignore it, and we're just going to say proportional to. And at the top, what you'll have product. So you're going to have lambda, and then product becomes a sum of yi's. And then product of e to the power negative lambda just gives us e to the power negative n lambda. And then, of course, you have this bottom part, which we ignore the constant here. Now, if you want to understand what would be the conjugate prior for this likelihood, you basically have to find some prior that has the form that resembles the functional form of the likelihood. So we need lambda raised to some power, and then we need exponent, and we want lambda here, or some linear function of lambda in the exponent. And there is a node distribution that has this functional form, and it's a gamma distribution. And so the gamma distribution is the following PDF. So that's a PDF of gamma distribution. You have beta to the power alpha, and beta and alpha are the parameters of the gamma distribution. Those are our hyperparameters. Gamma function of alpha. And then you have lambda raised to the power alpha minus 1 times exponent minus beta times lambda. So it's exactly what we want. We have lambda raised to some power, and then we have exponent of lambda, of linear function of lambda. So when you take a product of your likelihood, so that's the likelihood, and your prior, again, we're ignoring constants in the prior as well. So it's just an exercise now of summing up correctly the exponents. And what you have, you're just going to have another gamma distribution on the right-hand side. And alpha parameter of this gamma distribution is just the old alpha plus the sum across all of the yi's. And the beta parameter is n plus all parameter beta. And just to remind you again, a few facts about gamma. So a few facts about gamma distribution. So the domain or the support for gamma is all positive real numbers. The expected value of gamma random variable. So here we assume lambda follows gamma parameterized by alpha and beta. Then expected value of this lambda is just the ratio of alpha and beta. And the mode is the ratio of alpha minus 1 divided by beta. And the variance section is relatively easy here. It's alpha divided by beta squared. Again, so if you have some idea about what the variance and expected value of your lambda parameter is going to be, you can just basically reverse engineer the alpha and beta hyperparameters for your prior for the Poisson Gamma model. Let's do an example. We'll look at an example of beta binomial and Poisson Gamma models. And it's an example of analysis of clinical trials from paper by Novick and Grizel. This is a relatively old paper, it's 1965. And there are 4 treatments for duodenal ulcers. Treatment A B, C, and D. And doctors assess the state of the patient and try to identify which treatment is superior. And let's say you have sequential data, so data arrives in batches, and you can only look at pre-specified times at the data. But let's say, so you receive the data, and here are the outcomes of 4 of those treatments. You have 3 possible outcomes: excellent, fair, and death. And there were 100 people that were in each of those treatment groups. If you sum up all the values here, you'll have 100 people in each of those groups. So there were 400 people total in this study. And if you try to understand which treatment is better, for example, treatment A or treatment C, then basically you cannot discriminate them using traditional frequentist analysis at the 5% level. We're gonna try to do the same analysis using the conjugate binomial beta model, and then we're gonna do sensitivity analysis. We'll compare binomial beta model with Poisson Gamma model. All right, so let's do the binomial beta model. So let's say we have P sum index I to be the death rate proportional under treatment I. And if we want to compare the treatments A and B, for example, what we're interested in the posterior probability, but instead of posterior probability over each of them separately, we want to know the posterior probability of P1 being greater than P2, given the observed data, the table that you saw in the previous slide. And we're going to use the beta prior here and assume that P follows the data follows binomial distribution, so we're going to be doing inference about those parameters PIs. And you remember that expected value of the binomial distribution is alpha divided by alpha plus beta. And the posterior beta is the initial hyperparameter alpha plus the sum of all the observations that you have. So, and in our case, we had 7 positive cases, so the sum equals to 7, and then n equals to 100. So we had 100 cases in each of the treatment minus 7. And if we use hyperparameters alpha beta to be equal to 1 for our prior, so remember that's a flat prior from 0 to 1. And this is beta over p with parameters 1 and 1. And so we can calculate the posterior for treatment A and treatment B. For treatment A is 1 plus 7, 8, and then 100 minus 7 plus 1 is 94. The same calculations for the second treatment is beta 2, 100, which is the posterior distribution for this treatment. And now we can do the inference, so we can calculate the difference of 2 betas and calculate the probability that P1, which is, you remember, this one is beta distributed, this is a beta distributed variable. So the probability that one is greater than another, so treatment A is death rate is greater than death rate of treatment B is roughly 98%. So it looks like we have a rather strong evidence that treatment B is better treatment. So you see you have only 1 death case here and you have 7 death case here. And so the model says that the probability of having something like that under this model is 98%. And of course, whenever you choose the prior model and your likelihood, you always have to question whether those choices were correct choices. Sometimes those choices are made out of convenience. For example, when we want to achieve conjugacy, we choose the prior and likelihood, so we have the analytical form for the posterior. Sometimes it's chosen just because the modeler decided that the data looks like something that like a Poisson likelihood or binomial likelihood. But it's always a good exercise to do what is called sensitivity analysis. Sensitivity analysis is a simple exercise to check what happens if you choose a different model. You can choose a different likelihood, you can choose a different prior. And in this case, we try different likelihood, we'll try Poisson likelihood. And for us to get the conjugacy case, we gonna switch also the prior instead of the beta. We're gonna be using the gamma prior, and it is the same data set that we're gonna analyze, but now we're gonna assume that the death rate follows a Poisson distribution parameterized by lambda uh, by the rate, and we're gonna choose the prior gamma with some hyperparameters m and z, and then what we can do, we can calculate the probability that the ratio of two of the lambdas is greater than 1.3. Again, you remember that the posterior distribution for lambdas, distribution for lambda I, given data is gamma distribution, and we know how to calculate the parameters of this gamma distribution. So now we can take the ratio of two gamma distribution and calculate the probability of interest to us. And in this case, if we choose, so these three rows, three columns correspond to different values of m and z, the choice of initial hyperparameters. So if we choose m and z to be equal 0 to begin with, then we have 95% that lambda 1 over lambda 2 is greater than 1/3, and 88% under 102 assumption for the hyperparameters. And if you choose 205, then you get 79%. But the bottom line here is that, and if you choose to look at the ratio greater than 1.6, it's 91, 80, and 64%. Looks like for the choice 0, 0, that would be similar to the choice of 1, 1 for the beta prior. We have consistent results here. So our model, the Poisson Gamma model, tells us pretty much the same thing, that there's a heavy evidence that shows that second treatment is a better treatment.